This is the presentation for the paper High Resolution Additive Formwork for Building Scale Concrete Panels. Authors Roberto Naboni and myself, Luca Breseghello, from CREATE, the Group for Computational Research in Emergent Architectural Technology, established within the section of Civil and Architectural Engineering at the University of Southern Denmark. For 2015 only, concrete can be accounted for 2.8 billion tons of CO2 emitted on our planet. And if we project this to 2050, concrete and its production will have caused emissions for 470 gigatons of CO2 in the world. On the other hand, formworks manufactured with conventional technologies can impact for over 50% on the cost in conventional concrete structures and for about 90% within non-standard structures. For these reasons, both academia and practice are exploring different approaches for changing the way we build in concrete, from milling and hot wire cutting to the use of textiles, but also moldless solutions such as slip forming and steel mesh molds. The presented research focuses on the use of additive manufacturing technologies to produce concrete formworks. And a series of projects explored various approaches in this field, from fused deposition modeling to sand-based and wax printing. And in the attempt of exploiting the fluidity of concrete, our approach is that of combining the formal freedom offered by FDM 3D printed thermoplastic formworks with ultra-high performance concrete and short steel fibers. The aims of the research are those of developing a consistent workflow of design, fabrication, and analysis of the use of additive formwork for complex concrete panels. That of studying the relationship between geometry and manufacturing method, highlighting its opportunities but also its limitation. And this is done realizing an experimental proof of concept, the design and manufacturing of a series of concrete panels with high resolution informed textures. And a first preliminary experiment is carried out to study and evaluate a set of thermoplastics to be employed in the formwork 3D printing process. The selected polymers for this test are polylactic acid, PLA, ABS, polypropylene, and PETG. For all the materials, a specimen of 500 by 500 by 40 millimeters was printed and evaluated following multiple criteria: ease of printing, precision, and mechanical resistance, using different methods: thermal imaging, 3D scanning, and a visual assessment of the printed specimens. All the objects in this and the following part of the experiment were printed using a large volume Delta 3D printed with a pellet extruder and a 3 millimeters nozzle. Thermal monitoring of the prints gave indications about the rate of cooling of the different polymers, which demonstrated to be a factor in the shrinkage and deformation of the specimens. Via 3D scanning, the specimens are compared against the digital model, where ABS and PP presented high deviations due to their high material shrinkage. The table presents the deviations along the different axes, highlighting higher global and percentual deformations in the short section of the specimens. And the deviation distribution, here illustrated, confirms the difference between PLA and PETG, which presented deviations smaller than 4 millimeters, and ABS and PP, which have peaks of over 13 and 27 millimeters respectively. Given these analyses, the chosen material for the design experiment is a PLA pellet derived from industrial production waste, which holds mechanical and physical properties comparable to conventional PLA. The second part of the paper presents a design experiment for the fabrication of 8 individual panels with 500 by 500 millimeters dimension using additive manufacturing formworks. Each panel is characterized by a highly unique surface texture, which tackles and design and fabrication issue with the goal of exploring, analyzing, and assessing the formal possibilities and limitations of the manufacturing approach. The developed design and fabrication workflow is characterized by two intertwined streams: the flow of data and that of materials, which inform each other from the computational design through the additive fabrication of the formwork and to the casting of the concrete panels. Additionally, on the one hand, data feedback is obtained through the 3D scanning and can be transferred in the next design iteration. And on the other hand, the plastic formwork can be reused or shredded and recycled for printing. Computational modeling of the highly unique textures of the 8 panels is combined with the analysis and control of their morphological features. The 8 panels differs in the distribution of curvature and in section thickness, but they also present topological variations as well as smoother and sharper edges. Together with that, a set of digital analysis tools were developed and used to have a live feedback during the modeling phase, checking for mean curvature and section, as well as fabrication parameters such as printing and demolding angles. Through the optimization of the printing toolpath, avoiding discontinuities and reducing its overall length, the 8 formworks were printed in pairs with a layer height of 0.6 millimeters and a width of 4.5 millimeters for an average weight of each formwork of 2 kilos. These settings allow to print at high resolution, yet providing a good mechanical properties to the plastic molds. The printed forms are then separated and placed horizontally in a set of modular wooden frames. A total of 220 kilos of CRC self-compacting mix were then poured in the 8 molds, and after 72 hours, the formworks were removed from the wooden frames and the concrete panels extracted from the formworks. The panels were successfully demolded and filled the complex geometries of each of the formworks. And here it is a section of one of the panels highlighting the variation and control over the thickness that here it's ranging between 25 and almost 100 millimeters. Both the formworks and the final concrete panels are then 3D scanned with the structure light technology and compared against the digital model. From the scanning, a total average deviation of the formworks of about 1 millimeter can be observed, and this deformation occurs mostly along their longer face towards the center, and that's a consequence of material shrinkage. In the concrete panels instead, P4 and P7 present deviation peaks at 8 millimeters, but an overall average deviation of the concrete of 1.5 is registered. As you can see here, P3 and P8 present deformations in the barycenter, and that's possibly due to the pressure exerted from the fluid concrete on the molds. The project demonstrates successful results in manufacturing concrete panels with highly unique geometries and design features to the scale of 3 millimeters using additive FDM formworks. From the analysis and comparison of the fabrication method and the digital model, we can generally observe that a combination of high printing angles, steep demolding angles, and curvature complicates the demolding and impacts partially on the manufacturing quality. Future outlooks of these projects are testing recycled thermoplastics from used formworks, developing a simulation of the mechanical behavior of the complex formworks for geometric optimization as well as placement of reinforcements, improving the design for the molding, and scaling up the experimental setups, and integrating reinforcing bars. Thank you for your attention.